Welcome to this lecture series in linear algebra. In this lecture, we'll look at a more general version of the first isomorphism theorem, or what I am just dubbing as revisiting the first isomorphism theorem. In this lecture, we'll not see any applications of it, but as time progresses, this will be a very useful thing. Okay, so what do we need to know? We need to be familiar with set theoretic quotienting, the first isomorphism theorem, and quotient spaces. If you understand these things well, then you will easily be able to follow this lecture. So let's mark these things and move on. Here are some problems for practice. And now let us get started. So before we revisit the first isomorphism theorem, we need to revisit the set theoretic version of it, which is as follows. So suppose we have a set X and a set Y, and we have a map from X to Y, and suppose there is a relation. So let this be a relation on X this be an equivalence relation, not just some relation on X such that this guy is finer than the fiber relation. What does that mean? If you remember from the previous lecture, this just means not the previous lecture, the lecture on set theoretic quotienting. This just means that each equivalence class under this relation is contained in some fiber. That's what that means. So if these are all the fibers, then the equivalence classes under this relation may be described via this diagram in this way. So each thing is an equivalence class, right? All of these things are equivalence classes under this relation. So we saw that the map F factors through the set of all the equivalence classes to yield this map F bar, which is as follows, which takes an equivalence class to the image of any of its representatives. Okay, so you pick an element here, it's going to be an equivalence class. You choose a representative of it, meaning an element in the equivalence class, and send it to the image of F under that. This is well defined. We talked about it at length. So this diagram commutes. And if you think about it, this further factors through this object where, so this vertical map is the natural projection map, and this horizontal map is also natural projection in some sense. I will talk about it. So the vertical map pi sends X to its equivalence class under tilde. Maybe I'll decorate it with a subscript just so that there is no confusion. And the horizontal map capital pi takes the equivalence class of an element X to the equivalence class of X under the fiber relation. So this is the fiber relation, and I have decorated with tilde to denote that we are talking about the equivalence class under the fiber relation. In other words, this is the fiber which contains X. So that's the horizontal map pi, and the vertical map just takes an equivalence class, meaning a fiber in this case, equivalence class under the fiber relation to the image of any of its representatives. Image under the map F. So that's what that map is. We may denote it by F double bar or something. So this commutes. Okay, and just so that it looks a little bit more consistent, I will write this tautological thing. Looks a bit complicated, too many symbols in one diagram, but it is nothing. It's very basic. So yeah, so this is the revisitation of set theoretic quotienting, as we have already seen. We perhaps didn't see this part, but I hope all of this is now obvious. Okay, so now let's go back to linear algebra. So in the linear algebraic context, this is what happens. Suppose we have a linear map, and let U be a subspace which is contained in the kernel. Okay, U is contained in the kernel of T. Then the cosets of U, each coset of U is contained in some coset of the kernel. So let me write that thing down. So note that each coset of U is contained in some coset of the kernel. Kernel of T, of course. And now if you apply the set theoretic principle that we just discussed, we have this map T going from V to W. This factors through V mod U to give a map T bar, where this is of course the natural projection which takes a vector V to its coset, and this takes a coset to the image of any of its representatives under the map T. That's it. That is the more general version of set theoretic quotienting. More general version of first isomorphism theorem. This is not necessarily an injective map. This will be injective if and only if U is equal to the kernel of T. And just to complete this diagram, this further factors through V mod kernel of T via this map, which we may write T double bar. The horizontal map takes a coset of a vector V. Well, how should I say it? It is a coset of U whose representative is V to the coset of the kernel whose representative is again V. So that's this map, and T bar takes a coset of the kernel in this fashion. Just pick a representative and output the image under T. So it's just the same diagram as we drew in the previous page in the set theoretic context. Instead of that, we have all linear maps. Everything here is linear. That's all. This is linear, that is linear, everything is linear. So nothing new here. It may seem a bit complicated though, but what can I do? It's not really complicated. Okay, so let me finish with one more concept. So fix an endomorphism, not some linear map, but an endomorphism of a vector space. We say that a subspace U of V is T invariant if the image of U under T is contained in U. That's the definition. Very simple. Let's see examples, at least 2 examples. So the kernel of T and the image of T are both T invariant, as you can easily verify. All right. Now, here is the very important thing that I want to note. We have this map T going from V to V. Apply the natural projection onto the set of all the cosets of U. So this is the natural projection. And now this composite, which is pi composed with T, this composite kills everything that is in U. So what I'm trying to say is, if little u is chosen arbitrarily in U, then this thing is equal to 0. And by 0, I mean the 0 of V mod U. Why is this 0? Well, since this is T invariant, this is lying inside capital U. and therefore it is killed by the natural projection map. So in other words, U is contained in the kernel of pi composed with T. Okay, and now by what we just learned, the map pi composed with T therefore factors through V mod U. To give another map, which we may denote by whatever, I will call it T bar. This may look like an abuse of notation, but that's okay. I will call it T bar in this context. And what is the description of T bar? Well, you start with a vector V, you map it to, so let me maybe repeat this diagram. So you start with V, under the map T, it goes to T of V, then it goes to TV plus U, meaning the coset of U whose representative is T of V, and therefore under this diagonal map it goes there. Here it goes to V plus U, the coset of U whose representative is V, and that's the description of T bar. You pick a coset, find a representative, and apply T to it. We do not need to check well-definedness of T bar anymore. We have done all that work. Whenever we have a linear map such that this guy is contained in the kernel of that, it factors through the correct thing, and all of the well-definedness has already been checked. So we do not need to check well-definedness again. So what is the upshot? The upshot is, if you have a linear endomorphism and you happen to find a T-invariant subspace, you can create another endomorphism. This is the induced endomorphism on the quotient space. So if you write V mod U as V bar, this looks very nice. We started with something in this space and we ended up with something here, right? Where V bar has to be understood. V bar is V mod U. So, I mean, it's not like we have a map from this space to that space, so let me not draw this. What I'm saying is, we started with something in end V, and suppose U is T invariant, then we get something in the quotient space. And this is very, very useful. A lot of linear algebra is about studying endomorphisms. So you want to prove some property of an endomorphism. What you might do is, suppose you're lucky to find a small invariant subspace, then you will have a endomorphism on a smaller dimension subspace. And then by some inductive reasoning, you may assume that the property that you wanted to prove for the original endomorphism holds for this new endomorphism, and then you may be able to lift this property for the original endomorphism. And this is a very common theme of reasoning in linear algebra. So this we need to keep in mind. Okay, so just remember everything in this diagram. The entire thing should be very, very clear. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.